Okay, what does this possibly have to do with computing? So you go back a few decades, this is the ENIAC computer. This was one of the first general purpose programmable computers, very successful numeric integrator. But while it was being built, von Neumann and some others, partway through its construction said, wait a minute, we made a mistake, we need to change the architecture. And it was too late, they were already too far along in this, they finished building the ENIAC as it was. But they were unhappy with it, they wanted something different. They wanted a second generation machine. Now what was wrong with the ENIAC? If you look up close in the back right corner here, you see all these cables and you see all these knobs. That was the program. Okay, the program was not software. The program was this physical stuff, these cables, the holes that they were plugged into, the positions of these knobs. That's what told the ENIAC what to do. That was its instructions. And so the program was hard. And what von Neumann and others wanted to do was they wanted to take the program and make it modifiable. They wanted to store it in the same place that they stored the data, the numbers. And that led to the creation of the EDVAC and the EDSAC, and it basically led directly to things like Pentium. Now what's interesting about a stored program computer, this was the initial bootstrap program for the EDSAC. This is the initial orders version 2 in 1949. It basically, I think it read off punch tape. But it basically goes through and it reads data, it modifies it, it writes it back in. The interesting thing to note is down here in instruction 18, it says take the contents of register F and transfer it to memory location 20. And memory location 20 is right here. It's in the instruction space. And 2 steps later, this instruction is going to be something different from what it originally was. So this is a self-modifying program. And there's 2 things that I like to think about with this. One, normally you think of code as acting on data. So code is sort of the subject of some action, and it acts on the data, which is the object. But in this case, you have data sort of acting on the code. You have data actually modifying what the code is that's going to be executed. So that's the first thing to think about. The second thing is, if you look at the contents of register F, you see a bunch of 1s and 0s. You can't tell if it's data or code. You don't know if it's a number, you don't know if it's a set of Boolean flags, or you don't know if it's an instruction. There's no way to tell. It depends how it's interpreted. Okay? So keep that in mind. We're going to come back to that. Let's skip ahead about 5 decades and look at Java. So Java, basically, you take a program, you run it through a compiler, it produces bytecode, which is machine-readable versions of your original program. And then you feed that into some kind of Java engine, a Java virtual machine. And all of this is probably running on some workstation. And then the JVM executes the bytecode. And when it's executing it, you basically have the bytecode version of your program, feed in some inputs, generate outputs. Very, very basic design. What happens, though, if the program you're running in here is a Java compiler, and your input is a Java program, and your output is bytecode. Now that's perfectly legitimate. You can write anything in Java that you can write anywhere else. So you can write a compiler. And now you get bytecode out. So what would happen if you wanted to execute that bytecode? If you wanted to see what it did, if you wanted to analyze it somehow, you want a Java program analyzer. How do you execute this bytecode? Well, there's no way to get this bytecode back inside the JVM. That would actually be a big security violation. But what you can do is you can also write a JVM in Java and run it on your JVM and feed your bytecode into there. And now you can do analysis on your program, you can do performance analysis or whatever it is that you're interested in, by building this new JVM inside the original one. And so what you have pictorially is your original JVM X, and inside there you have a new virtual machine X prime that you built. And that's great, but what if you're running a compiler on X prime and you want to analyze the output of that? Well, you can build another virtual machine inside X double prime and another one inside X triple prime, and you sort of get this never-ending descending chain of virtual machines where you're trying to analyze something about yourself, but instead of analyzing it in yourself, you build a copy and you analyze it there. And that works fine unless that copy is going to do the same thing. And then you get into this kind of infinite descent. And this is an example of a dualistic view of things where subject and object are very different from each other. The program on here is trying to analyze the program on there. And this ties into a number of different things. Cantor in the 1800s came up with a technique we call Cantor diagonalization to actually was trying to show that there were more real numbers than there were integers in some precise way. And he came up with this technique, which turns out to be very applicable to a wide range of questions. For example, there's this I am lying paradox. You may have heard this. So I make a statement to you, everything I say is a lie. And then I say, I am lying. And you try to analyze that. Well, if I'm actually lying, then I just told you the truth, that I said I was lying. And if I'm telling you the truth, then I was lying when I said everything I say is a lie. And so I must have been lying, but if I was lying, then I was telling the truth because I said I was lying. Go down this never-ending chain of contradicting yourself, and you never come out. And so you can't analyze that situation as some kind of paradox, which was actually used in the Star Trek episode to cause a meltdown in the brains of these androids that were going to take over the Enterprise. And they used that exact riddle on one of them, and smoke came out of its ears. And